On the test, what I'm actually going to give you is a problem that has a molecular formula and a proton NMR spectrum. So it'll be something like this, where you'll get the spectrum and the molecular formula. There are 7 steps that I want you to follow when you're solving these kinds of problems. First of all, find the double bond equivalence. Secondly, identify the pieces that can be seen by looking at the integration. So write down the pieces that you can actually see based on the spectrum. Thirdly, figure out what you're not seeing by subtracting the pieces you can see from the molecular formula. The structure then will be made up of the pieces that can be seen plus the pieces that can't be seen. Draw possible structures that can be made from these pieces, and then use chemical shift and multiplicity to figure out which possibility is correct, and finally verify your structure by assigning each hydrogen on the spectrum to a hydrogen in the compound. Alright, so let's go through this and see an example of it. So here's our spectrum, here's our molecular formula. Step 1, we find out the number of double bond equivalents because that will help us put it together. C5H10O becomes C5H10 because oxygen doesn't figure into the calculation. This becomes C5H12 because 12 would be the number of saturated hydrogens when the number of carbons is 5. For more information about this, please go back and take a look at the units of unsaturation mini lecture if you haven't already seen it. So the way to figure out the double bond equivalence, 12 minus 10 divided by 2, that gives 1. So we know there's at least one, there is one double bond or one ring in this compound. The next thing we want to do is see what pieces we can actually see based on the integration. So that's when we just look at the integration and we see what these groups probably are. So if we've got 3H, that's going to be a CH3, 2H, that's going to be a CH2, 3H, that's going to be a CH3, and 2H, that's going to be a CH2. This is all based on what I've got here on this slide under integration. So the pieces we can see are these, CH2, CH3, CH2 and CH3. But this isn't everything that's in the compound. So what I'm going to do is I'm going to take the molecular formula, C5H10O, and I'm subtracting out everything that I can see based on the integration. Now if I take 5 C's and I subtract out 4 C's, I'm going to be left with 1 C, I'll be left with 1 O, and you'll notice all the hydrogens will be accounted for. That's 10, there's 10 here as well. And there's no double bonds anywhere in here, so the double bond must be somewhere else in the compound other than with these CH2s and CH3s. So what we've got left is a C, an O, and one double bond equivalent, which probably means we've got a C double bond O. Now the question you've got to be asking is, why doesn't the C double bond O turn up in the proton NMR spectrum? Why don't we see it there? The reason, and it's a really good reason, is that the C double bond O has no hydrogens attached to it. If it had any hydrogens attached to it, it would turn up somewhere in the spectrum, but it doesn't. So this is the importance of taking the original molecular formula and subtracting out what we see so that we can figure out what we're not seeing in the spectrum. So what that means is that the whole compound must be made up of what we see plus the thing we don't see, which is the C double bond O. And you might be wondering, well, how do I know how many bonds to put on each of these groups? Well, we do that based on how many bonds carbon can actually have. If carbon has 4 bonds and there are 2 hydrogens here, that means that it must be bonding 2 times to something else. A CH3 will have 1 bond based on the same thing, and the C double bond O, since we see 2 bonds here, must be bonding twice to something else. Further, we know that what it's bonding to cannot be hydrogens, because if it was hydrogens, then we would have seen it somewhere in the proton NMR spectrum. So these are the 2 possible structures that we could come up with that have 2 CH3s, 2 CH2s and a C double bond O. and does not allow us to put an H on the C double bond O. So these are the two that I could possibly come up with. Now what we can do is we can actually figure out which one of these actually belongs to the spectrum based on symmetry alone, because I can label each of these. It'd be A, B, C, and D, so it'd be 4 different hydrogens, which means there should be 4 different peaks in the compound. If this was it, then there would be A, B, B, A, so this would be a plane of symmetry. There would only be 2 peaks because there's only 2 different kinds of hydrogen in this compound. So I already know that this one, since it's got 4 peaks, must be this compound right here. So that's going to be our answer. Now what we can do is we can assign this based on what we're seeing in the spectrum and what we see over here. Alright, so the 3H has to be, this 3H has to be a CH3. And if I've labeled this A, B, and C, and D, I can figure out which CH3 this actually is. Now what I do is I've got the CH3 here, and what I see is 3 peaks. And the rule is this: if you see N peaks, then there are N-1 hydrogens adjacent to that CH3, or N-1 hydrogens on adjacent carbons. So we've got 3 peaks, which means there must be a CH2 next door, and that's it. So this must be A. If we take a look at the other CH3, we see 1 peak. 1 peak suggests there are 0 hydrogens on adjacent carbons. That means that this must be right. See D, which is CH3, and there's no hydrogens attached to this C double bond O, so this comes up as a single peak. We can look at the CH2s as well, and this CH2, if we concentrate on this one has 3 peaks, which means it's got 2 hydrogens on an adjacent carbon atom. So which one would that be? Well, this CH2 has 2 hydrogens on an adjacent carbon, so this one must be C. This one has 1, 2, 3, 4, 5, 6 peaks. That means there must be 5 hydrogens on adjacent carbon atoms. That means that this must be the CH2 that we're talking about, so that would be CH2 number B. The other thing that can help us to assign these is that looking at C and B, the closer that a group is to an electronegative group like C double bond O, the further downfield that peak will be. So I'm looking at this, I see C double bond O and I see C and B. Since C is closer to C double bond O, I'd expect it to be more downfield. That means more to the left. And if you take a look where C and B are relative to each other, that's due to the influence of the C double bond O. Looking at the CH3s, you can see the CH3 that we've labelled D is closer to the C double bond O than the CH3 we've labelled A, and that's borne out by the spectrum as well. You can see that D is downfield from A because D is closer to the C double bond O than A is. And that's always a good thing to look for when you're trying to assign spectra.